Very good. So the purpose of this presentation is to talk about microgrids and some little work that we have done on microgrids in terms of analysis and actual experimentation. So when I started my master's, my master's was on reactive power optimization. I think during those times, everybody did reactive power optimization. But so for that, we required a test system. So standard test systems were a 6-bus Warden-Hale system, or a 14-bus system, or a 30-bus, I forget, 30-bus, and 118-bus system. You don't have a similar test system from IEEE for a microgrid. With AC and DC, unbalanced three-phase, it doesn't exist. You have test systems for distribution systems. You have, a 13-bus system, an unbalanced open delta Florida system. There are many of those systems. But what we lack is a microgrid test system. So our interest was to create some kind of a tool which will enable test system analysis and also do some kind of a lab demonstration where we can validate our results from the analysis tool with the lab model itself, so that we can say, well, our analysis tool works perfectly and it duplicates what the lab model has. So in our minds, just to have a clear context, a test system for a microgrid should have an AC three-phase network, which is the backbone. It should also have single-phase loads and generation on the network. So that's a key thing. So it should be an unbalanced three-phase four-wire system. That's really what we think should be the AC portion. Then you should have converters which link to DC sections of the microgrid, and we envision several DC sections. So you have a microgrid where you may have several AC sections and several DC sections interconnected by converters, where power might flow either way, from the AC to DC or DC to AC. And the analysis tool should be able to analyze it. You should be able to have a slack bus on the DC instead of having a slack bus on the AC system. So those are the nuances that we thought we should be able to capture within a microgrid. Have a implementation tool or analysis tool which will be able to analyze such a network, and also have that as a practical model where we have it set up in the laboratory or in the field, and be able to validate results, the numerical results which we get in the computer through our simulation, and what we get from the lab, right? That's the purpose. So we started on a 2-year journey. So there are multiple sponsors for this network. So all the work is done by this person here, Dr. Banu Apatela. He did all the analysis and all the lab models and so on. I just wrote on whatever he did and put my name on top of it, okay? So just to make it clear, the context of who did what and who's claiming to have done what. Okay, so he's a research fellow at the Center for Urban Energy, and he did bulk of the work that is being reported here, if not all. Also, there are several people who have helped us in the process. So the physical implementation required a laboratory setup. So Schneider Electric provided or helped us to create the lab, and the person who helped us was Mr. Riburu. Then, so the lab setup was created with money from Schneider Electric, and then we also required to buy equipment to create the actual microgrid. For that, PowerStream funded us to a tune of $200,000. So we got money from them. I'm sure you're excited to be partnering with them. Well, so we've milked them before, and we've and gotten money for the microgrid implementation. I will walk through it. Then there are a couple of people at the center itself who have helped us significantly. So Bob Singh is is a fellow at the center who has helped us with realities of actual systems, so that when we create a system, it doesn't deviate from the codes and standards very much. So he's brought in his utility experience into it. And Kathy Kuto is a lab engineer in the lab who has actually done all the connections and made sure things don't smoke, which we like to do oftentimes. All right. So also I report here analysis tools. So this analysis tool was its development was funded by Semiconductor Research Corporation in the US. So they gave us some money to hire people and develop the analysis tool. So the analysis tool development was funded by them, and the physical implementation, as I just said, was shared between Schneider Electric and PowerStream, right? So I hope I've given appropriate credit. So the purpose was to build an analysis tool. So if I take a common analysis tool such as SIME or PSS SynCal, you cannot actually model what we have modeled here as a microgrid that I explained to you and analyze in SIME. So which is why we say, well, it's not possible to use a commercial tool at this time to analyze a microgrid in its entirety. And that's a challenge which we thought we will overcome from our research. And also build a lab scale model which will be able to show and compare and say that our analysis tool is accurate. So those are the two things that I will be presenting, and just to give appropriate credits, the first topic is funded by SRC from the US, and the second is funded from PowerStream and Schneider. So the first thing that we wanted to do was, if I describe the three-phase AC system and a DC system, AC-DC power flow has been existing from, let's say, 60s. And HVAC, HVDC systems have existed for a long time, and those analysis tools could also be used effectively for analyzing microgrids. So what are we reinventing here is a quick question that we always would like to ask ourselves. So the thing that we found out when we looked at those AC-DC power flow methods were that it was not standard to bring in a power converter which converts AC to DC or DC to AC into the Y bus. That's not a common thing. So you have additional equations which you satisfy in the power balance equations, and you can use Newton-Raphson to solve and find a solution. What we thought was, well, we have all the elements in a transmission system modeled as pi models. So if you have a transmission line, you make a pi model out of it. You have a transformer, you make a pi model of it. And why can't we make a pi model of the power converter as well? And so we said, let's try to do just that. So, so what we did was I'll just flip to the next slide here. So this is a power converter, and in this power converter we have AC. And also when we realize, or whatever model that we do and we realize that model, we wanted that model to be capable of analyzing unbalanced three-phase system in addition to analyzing three-phase balanced systems. So if you look at all the HVDC models used for transmission system power flow, they were all three-phase balanced systems. So that nuance also has to be factored into it. So this is an ideal converter which is converting from AC to DC. These are three impedance values within the converter. This is the AC side of the converter, and that's the DC side of the converter, and the losses are accounted here for the conversion. Right? So this is a very simple model. This model has existed in literature for a while. So what we did is we took this particular model and we said we are going to analyze this model to see how it functions. So that was the first thing that we did. Then what we wanted to do was to create a pi model. And so this is our pi model that we propose, which will be able to model that power converter, and we can take this pi model and include it into the Y bus. Now the catch here are that there are two types of converters, and don't test me on power electronics. That's not what I I profess to know very well. So there are two types of converters, and one where you can set the conversion values, which is how much, what is the voltage conversion value, and so on. So we have assumed that we'll be able to set the conversion value of those converters, AC-DC converters, and that gives us an ability to freeze this into a pi model. It's just like a transformer. So if you take a transformer, in a transformer we should be able to set the tap, and the tap might be a complex value, might have a magnitude and a phase angle. So in a similar thought, if we have a conversion factor, then that conversion factor, if it is a controlled converter, we would be able to set those values, and those are the values right in here. And so with that, we derived a bunch of equations which allow us to take this converter and model it as a pi model. And in doing so, if the conversion is complex, then you will get two sets of impedance values. When you're looking from the AC bus, those are Y1, A, B, and C. If you're looking from the other side, which is VJ, which is the artificial bus that we create, then you will be able to get the impedance values as Y2A, Y2B, and Y2C. So with this, what we can do is within the same Y bus, we can have AC equations, we can have DC power balance equations, and we can have terms which enable us to connect AC and DC. So that is what this Y bus, this pi model of the converter enables us to do. So once we put that in, then it becomes very simple, right? It is just a regular power balance equation with the Y matrix made out, where wherever you have a converter, the pi model of the converter is used to populate those terms of the Y bus. So now I can write the whole power balance for the entire microgrid with AC and DC, where AC is three-phase and you have DC buses as well in the DC network, and the pi model is able to relate or connect the AC buses to the DC buses, the pi model which we proposed just now. And that allows me to have a single set of equations as power balance equations. And then I use the regular Newton-Raphson method to solve it and find a solution. I hope that's okay, right? So that's simple and straightforward. So that's the first thing that we did. Then what we did is we took a modified, or we took the 13 bus system, test system, which is available in the website for distribution system analysis subcommittee of IEEE. So they give this 13 bus. We took this 13 bus system and we said we are going to analyze it. Now in order to analyze it, we have a couple of DC elements. So you can see in here, I have a converter 1 which is able to convert from AC to DC. Then I have distinct buses and I have a energy storage. Energy storage is just a simple P or Q, so there is no complication in there. But this line is a DC line. Similarly, this line is a DC line. And then I have another converter here, but in this case, this is single phase converter, and then I have a bus here, I have another bus here, this is a DC line. So this is my microgrid. So it has three-phase AC network with single-phase AC systems wherever, and then it has converters, three-phase to DC, single-phase to DC, a DC network, an AC network as well. So all the different things that you want to have is all in here. And then we use our method to analyze it. So this is the actual test system that we use, and it's based upon whatever we have in here. So I'll just flip by, and then so this tool is able to analyze the network and provide us with solutions that we chose to have. Now once we have the AC-DC load flow, what we could also do is take the same set of equations, pose those equations as constraints, and then you can optimize to whatever you want within the AC-DC network. So we can create an optimal power flow tool in a very easy fashion. So that was the next step that we thought of doing. Now, the purpose of that optimal power flow tool was to plan for the network, to optimally run the network so that you can have minimum cost or minimum generation. So those are a few things that you can do. What we could also do is, once we had this pi model and the Newton-Raphson based solution for a AC-DC network, we could also do probabilistic analysis of the microgrid and also plan for the microgrid considering a probabilistic scenario. So that was the next thing that we could also do. So in order to so basically the purpose of the SRC contract was to be able to look at a probabilistic scenario of different renewables and use that to size energy storage. So our development of the pi model ultimately led us to having that tool where we could do a probabilistic scenario or scenario testing of different renewables and combination of different probabilities, and then size different values of energy storage boxes so that we can maximize energy used from the renewables and minimize the amount of energy that we consume from the grid. So we tried it with multiple different objectives, and those results we are yet publishing. So we did publish the microgrid analysis tool, and we are still trying to publish the optimization results as such. The challenge that we are facing in publishing the optimization results, I will tell you, is that in the older works which people do, they don't have the pi model, but they find the optimal setting of the converter. So that could be very easily included in the optimization model. So the question that we were always asking ourselves is, what is it that you cannot do without the pi model that you can do with the pi model? And that distinction is not very clear to us. So we are still in the process of discovering that, because we are very sure the reviewer is going to ask us the same question.
So if you have the controllable things, then your Y-bus matrix becomes a unknown matrix.
A Y-bus, so if I know, it's just like a transformer tap. If I know the tap value,
then it is fixed.
So then Y-bus is a constant matrix.
If you don't, then
if I don't know, then Y-bus has unknown elements. So we assume that we have only those converters modeled, modeled in the Y-bus for which we can specify the control the control value.
Have you tried determining those through optimization?
Yeah, you can very easily do that.
No, the control variables which are not within the Y-bus.
Yeah.
By optimizing those.
Yes. Yes. So it's just like the reactive power optimization where we find optimal tap setting. So very similarly, we could do it, but then you don't need the pi model to do it, because you can have other models and add them as additional equations. Okay. So in our minds, you're asking, well, pi model is just another mathematical representation, but doesn't get us any technical benefit. So it's just like trying to represent the transformer as an additional equation. So it doesn't get us, instead of using it as a pi model, which is what the industry standard is. So that is where we were lost a little bit.
You were saying generating the scenarios for probabilistic part.
Yeah.
But how can you make sure that the Newton-Raphson will work for all kinds of scenarios?
Oh, because that is. Yeah, so we restrict the probabilistic scenarios to those which are feasible only.
Newton-Raphson is for solving the power flow.
I know, but you have found randomness that is random variable generator, which eventually the Newton-Raphson.
If we exclude those where we cannot add up generation and satisfy demand, then we'll say, well, these random generations are not satisfied, and then we'll leave it out.
I mean, that actually changes the probabilistic characteristics.
Yes. So he says, well, where there is infeasible, So you create all the random solutions, random generations. There might be a subset of that whole set which is not feasible. So you just delete that and then use the rest.
I mean, it's kind of, there's nothing else we can do.
Yes, there is nothing else because we don't want the process to get stuck with
Yes.
infeasible solutions.
But it's still a big million-dollar question how we can do that at the same time not changing the characteristic of original probabilistic information.
Mm-hmm. All right.
Well, Newton Russell will still converge. If it is an optimal power flow, then you get infeasible,
Yes.
even with the site.
Mm-hmm.
You'll get a solution of load flow. But if you have those voltage constraints and those constraints, then
That's the problem.
Yeah,
Yeah.
then you'll have infeasible.
All right. So, in order to check ourselves, in the first portion, we excluded the DC systems and got only the AC systems and checked our results with sine. That worked out. But there was no other way of checking the DC portions of the network, and so we were stuck there. So in order to overcome that, what we did is in the laboratory, we created a 16.5 kVA microgrid. And it's a 600 volt, 3-phase, 4-wire, unbalanced microgrid. And we also have a couple of other different supplies that come into the microgrid because we have to create PV. And to create the PV, I require a DC supply. So in the lab, we have 2 transformers. One transformer connects to the microgrid. The other transformer, we use it to have a rectifier and create a DC. So in case I require a DC supply to be inverted and supplied in as a PV, then I could very easily do it from the second transformer. So in reality, in the laboratory, we have 2 separate transformers. One transformer is dedicated to just create a DC source. So that's how we do whatever we are saying that we do here. We have, so it's a 3-phase unbalanced network that we have in there. There is a DC network section which we create in the lab. Then we also have single-phase energy storage with lithium-ion batteries. There are 3-phase loads which are just heaters. And then we can have the microgrid operate both in standalone or grid-connected mode. Both are possible. What is not possible is to automatically transition from grid-connected mode to the standalone mode. That we don't have the capability. So we have to turn the whole thing off and then turn it on all over again.
So when it is in standalone, it is supplied by a battery only?
It's supplied in the standalone mode. It is supplied from the DC, which acts like a PV, and the battery storage.
And how much load do you have?
We can create loads up to 15 kVA. All right, now this is how the load looks like, the system looks like. And I will just briefly explain what all of this is. So this is the grid supply right here. The grid supply is in the far right. It's a 600 volt, 3-phase, 4-wire system. Then what we have is a bus right here. So we call it a bus 200. These boxes are breakers, so which I can open and close. So from this bus 200, I have a transformer which goes to 208, and then one phase of it I take and connect to a converter. This is a Schneider converter which connects to a 4 kilowatt battery energy storage system. So I can tweak this to either be acting as a generator or as a load, depending upon my setting. Then I have 2 impedance boxes here which act as a feeder, 3-phase feeder impedance. So Z1 and Z2 are feeder impedance boxes. These are actually representing feeder impedance of power streams feeder in WAN from the Greenwood station, feeder M21. So if you measure impedance from bus 200 to bus 205, it will actually give you the whole feeder's impedance. And this bus 203 is a point where you get 2/3 load. So that's the point where that feeder has 2/3 load. And so it's split so that the total load can be seen here, 2/3, and the rest of the load is here. All right. So this Z1 plus Z2 together represents power streams feeder in Vaughan from Greenwood Station, feeder M21. Then I have here some loads. So there is a 3-phase AC load which is 5 kilowatts. Then I have a transformer, and the reason for us getting this transformer is we bought this inverter which is 3-phase inverter, and it's at 208 volts. So actually this is a 3-phase inverter, but it's 3 single-phase inverters connected together, and one acts as a master and rest of them act as a slave. So that is what we have as a 3-phase system from here all the way to here. And then there is a single-phase battery storage. There is a 3-phase load. Now this is a 3-phase converter. This side is DC. And we have a DC impedance here, which is acting like a feeder. And then we have a DC load. And then we have a DC supply. So this is a rectifier which is connected to another transformer right here, which we don't show. So the DC supply can go in, it can supply this demand, it can also supply this converter, which can send energy back. So during normal times, I have this breaker which is connected, closed, and I can supply all the requirements of load and generation and so on. During abnormal times, I can open this breaker, and all the demand can be supplied from this DC supply. All right. So we can operate the grid or the microgrid in both of those modes and have somebody manage it, right? So that's really how this is all configured. Any questions on the configuration itself? All right. So I have some visuals, some nice visuals. So this is the 3-phase inverter which we see here. This inverter right here is right here. Now this guy has multiple modes of operation. It can operate as a master or it can act as a slave. When it is acting as a master, it would supply fixed frequency and voltage. When it is acting as a slave, then we set the amount of power output and it would take whatever and supply that power output. So those are the two modes. So in the grid connected mode, this would act like a slave, so that whatever power we set to be wheeled from the DC will show up to the AC side. In the islanded microgrid mode, this will act as a master and set the frequency and voltage for the network.
So, Professor Bala, you would set the conversion value in this inverter?
Yeah. We set the voltage and then we will know the conversion value.
Okay.
All right. Then this is a single phase converter right here. This one. And then this is a Kokum battery, and we use this for a energy storage. This is a single phase energy storage which I showed as 4 kilowatts. And then here we have a DC line. So if you had thought of something fancy, it's nothing fancy. So one is a DC line, which is it's an impedance representing a DC line, and then another impedance representing DC load, which is 1 kilowatts. Okay, it looks like an inductor, but on DC it probably doesn't make any difference because it will just use that resistance value and show the impedance that we require to show. So we just wanted to make sure that we have a DC load, a DC line, and we represent this within the analysis tool, and we're able to find out the same value in the laboratory as well. These are transformers that we need to use because one part of the network is at 600, the other part is at 208. This is the DC rectifier which is connected to the transformer, and that transformer, the other transformer as I mentioned, and that there are two DC sources. One is a master, the other one is a slave. This I showed Z1 and Z2. So one portion of this is Z1, the other portion is Z2. And the cables go behind to connect to the main microgrid. So this is manufactured by a company in Guelph, right? So this is version 1 where the impedance is fixed. The next version we are buying, or nearly we purchased, and it is still being delivered to us. We can select the impedance value. So today the feeder can look like feeder in PowerStream. Tomorrow we can change the impedance to make it look like feeder in Waterloo. So it's flexible. So anybody can do an experiment with any customer. Just make it friendly. So then what we did is the analysis tool has to be verified. That's the objective. So power flow results from our analysis tool, and this is the actual measurement. So this is when the battery storage is charging, so it acts like a load, and this is when the battery storage is discharging, when it acts like a generator. So in both cases, we measured the errors and discrepancies that we were seeing. So in the charging case, voltage error in per unit is within mostly within 0.01, right? So which is about 1% error. This is when it is charging, and this is when it's discharging. So from our perspective, it is not a significant difference that we need to worry about. So here you can see we have AC buses all the way here, and then these are DC buses, right? So everything in per unit, and it just works. There's no issues to it. So just to be sure, the analysis tool uses the pi model of the converter. Oops. So I'll just like to summarize what we did. We first created a pi model of a controlled converter, included that in the Y bus. So I can now have AC-DC power flow where the Y bus is a constant, and you can have a regular Newton-Raphson to solve it. No complication of having additional equations. So the power balance equations will have AC as well as DC power balance equations. For the DC, there is no Q. Then, since there is no Q, you don't have phase angles as well. So it's just voltage and power. So the number of variables will be equal to number of equations. And then once we did that, we did a AC-DC analysis tool, and we sent that for publication. Then we have OPF tool. We're still trying to grapple on how do we actually present that OPF tool. Then we created a lab model to physically verify if our analysis tool actually pans out in the physical model.
OPF tool is on what platform?
Just MATLAB with fmincon. Because it's a bunch of nonlinear equations, power balance equations. Then we created a lab model. We did the verification, and that's it. So, thank you.
So the planning part,
Yeah.
finally you were identifying. So the 4 kilowatt battery storage, is it after doing the planning that is?
Oh no, it's the results of planning are not translated to the laboratory model.
Oh, this is
It's just to verify the analysis tool.
so that is kind of where the load is going further?
Yes, but for us, we just wanted to create a lab tool which will have decent current coming from the battery storage, decent current going into the load so that we can measure it and compare the analysis tool results. So our intention is to take this and actually see if we can create a standard test case. That is the intent of doing this exercise. Yep.
The battery here representing the source for renewable, for example, for the future.
Mm-hmm.
What about availability? For example, on peak, off peak for renewables is big matter here. renewable, for example, wind turbine at night will be during off-peak will be available maybe 90%.
Okay.
During daytime, maybe 20% or 10% or not available. How you can manage that as a variable?
For the analysis tool?
Yeah.
In analysis tool, I don't worry about what is not going to be there. For me, I'll know how much of generation is available, and we just input that as a input to the analysis tool, and it tells us, analysis tool is to find out a voltage solution of the network.
Yeah, but for example, if you decide to use, for example, 10 generators, 5 of them renewables,
Okay.
but the 5 of them renewables, depending on their availability, what time?
Yeah.
This is not going to be considered.
No. So we don't consider that. So the challenge that we are looking to address is if I know what is the amount of generation, I know it, then I want to analyze the microgrid, AC and DC, so that I can find its voltage solution. That's it. It's as small as that. I don't intend to predict or any of those things, just to create a robust analysis tool to find a voltage solution.
You were talking about optimized as well.
Yeah, in the optimization phase, we do a probabilistic scenario generation of different probabilities of generation from the different renewable energy sources. And then the objective is to minimize the total amount of power or energy that we need to buy from the main grid. Now, if I have more renewables, then and if I don't have sufficient energy storage, so I could increase renewables, but I might not be able to optimally capture that energy to supply to the demand. And then in case where there is no renewable energy generation, I'll be forced to buy energy from the grid. So we create different scenarios, and for those scenarios, we optimally try to size the energy storage box so that we can supply energy to the local loads within the microgrid. And so we just do a scenario analysis and size the battery optimally, so that we minimize. So the objective there is to minimize energy procured from the main grid.
Yes.
We can look at that in two ways. If it is a microgrid which is grid connected, then that could be an option. Not within Ontario because we have feed-in rates. But if it is a remote microgrid where you have the main grid represents a diesel generator and you want to minimize the diesel generation purchase, then that makes all the sense, because their diesel is like at $1.20 per kilowatt hour. So that's the rate at which you're buying diesel. So there it makes sense. If it is grid connected, probably doesn't make too much sense in Ontario case.
Thank you.
Yeah.
I mean, nice work. I just want to understand the scalability of the software.
Mm-hmm.
So you've done for, especially looking at the error. So are you confident that the errors don't grow as size grows?
Yeah, it won't grow because it's a regular Newton-Raphson load flow, and if you can scale it to 5,000 buses, it should still work. The scalability should not be a problem in this, because the Newton-Raphson solvers are pretty robust and it doesn't suffer with size. It might be a little bit slower, but it won't. The errors won't increase. You can comment about it.
But then it won't be a microgrid,
It'll be a microgrid.
No, I don't know. Like this is.
We'll get
I
back to
suppose
the
this is.
traditional system.
Is this a typical size or the one at the lab that you're using?
Well, there are a little bigger ones.
Yeah.
There is a Sigray microgrid, little bigger than this, but yeah, this is maybe a little bigger, but good enough. It's a good tool.
So the time for solution is like nothing.
And also, it doesn't depend. I'm not an electrical engineer, so I'm thinking about the strength of the. For example, here you can have a microgrid. At least they're asking for 10 megawatt solar, generation.
Computation will not be a problem for this.
So the size, the power source doesn't also affect the error.
No, it doesn't.
Okay.
It's not going to change it. Sir.
Excuse me. In standalone case, how can you define the slack bus for the full flow analysis?
Good question. So, in the standalone case, we need to have a slack bus. So our slack bus is bus number 320. Is right here, this bus. So the DC, because the slack bus should be able to give as much power required so that we can balance the network with all the loads plus losses, right? So it's just a mathematical convenience, just to make sure we are on the same plane. It's a mathematical convenience. So, and it's only for real power. So we assume in the standalone case, bus 320 is a slack bus, and it is able to supply infinite amount of power.
Okay, can this, I mean, this bus can be changed?
Yeah.
Because if we have like wind and the photovoltaic system at the night will be zero and the wind will be high in the night, will be high, and that makes the slack bus change with the time. Is this implemented in your lab or system?
So I'll answer your question in two parts. So in this network, when the grid is turned off, which is I open the breaker right here, the grid is turned off, then this three-phase power converter has to supply all the demand within this AC network. So it also will set the frequency and the voltage at this bus 209. And so whatever demand is there on each of those three phases needs to be satisfied here. One of the limitations is that if I put a large generator on one phase, this cannot act as a load for that particular phase while becoming a generator for the other two phases. That is a limitation. So we have to make sure that there is net positive demand on all the three phases by nature of that in converter design. So during that time, this source, whatever be the demand on the network, is going to be met by this DC source. So what we deem is that this DC source is the infinite bus, right? So if this acts as a generator sometimes, this acts as a load at some other times, we have to make sure that it is always within the boundaries of this generator acting as a source. Is that okay? Now this source might be supplying zero power because all the demand is satisfied locally by other generators. But that doesn't preclude it from becoming a slack bus. As long as the power sent out is not negative, the slack bus can still be functional. So let me go to the next portion of the answer. So if I have a system where I have a slack bus, I have demand, I have wind generation, at no time the slack bus can become a demand. So you will size wind generation such a way that it doesn't exceed the total load in the system. So the slack generator will still be the slack generator, but its output will become zero. Is that okay? Does that answer your question?
Another question.
Go for it.
You said you generate like many scenarios and you ignore the unfeasible scenarios.
Yeah.
Why you didn't consider like EG curtailment and load shedding for balancing?
We could do that too, but yeah, we haven't considered load shedding. We assume that all the loads must be served. Definitely, we could consider that too.
Back to the slack bus question. Now, you can assume this 320 as a slack bus because you have a stiff DC supply. Because you at the lab, the end it's connected to the grid, right? But in real situations where this is a PV, for example, can you still assume this as a slack bus?
Good question. So a slack bus doesn't mean it's a strong bus. Slack bus is just a mathematical convenience, right? So whatever it is, whether it's PV, whether it's a 1 kilowatt PV or in a 10,000 megawatt system, it could be still a slack bus as long as that 1 kilowatt the output of that generator is between 0 to 1. So it hardly makes a difference. It is just a mathematical convenience, right? So I could definitely have a PV which is not as strong. Here it is strong, but I could have a PV. So what I could also do is if I translate this guy to a PV, and that PV is like 10% of the total DC supply in terms of power, I could still have the other generator as well as a slack bus, as long as the output after the solution is within the range of that generator. Because I could have the strongest bus also as a generator, but if the solution decides to tell me that the output of that generator is more than its capacity, then also it's infeasible. So basically, when we solve power flow, the output decided from the algorithm should be within the generator's capacity. That's the only constraint. Whether it's strong or weak doesn't make a difference.
Because if it's can't supply the mismatch of power in the system, then it can't control the voltage and frequency.
Exactly. So it doesn't make a difference which generator you select as a source, whether it's renewable or any other, it hardly makes a difference, because after all, it's a mathematical convenience. Yeah? Okay.
Any other question? Well, thank you.
Thanks very much.